In our study of forces in the net force particle model, an important tool that we'll be using to study forces is something called a force diagram. A force diagram is something that gives us the direction, the relative magnitude, and the location of all of our forces applied to an object. So to help us understand force diagrams, I have an example here of a woman who is riding on a subway and she's holding on to the pole, as you can see. This subway happens to be accelerating to the right, and so we're going to have several forces acting on our woman. In our force diagram, we show only the thing that is our object. In this case, our object is the woman, so we've removed all of the outside things and have just shown the woman. And you'll notice that all of those forces are labeled as arrows, and they show exactly where that force is applied, or at least for the most part. This isn't a perfect diagram. So an example of a force would be the gravitational force, F sub g. Unfortunately, all of these labels are missing the vector symbol, but you remember that we know that we have a vector symbol on top of all of our symbols for force. And then also in our force diagrams, in parentheses, we've listed what is applying this force to our object, to the woman. So the gravitational force is a force that the Earth applies to our woman, and so we put the Earth in parentheses. There's also a normal force that the pole is exerting on her hand. And you may be questioning the direction of that normal force, but as you can see, her hand is kind of wrapped around the pole. So if I had something like this and I were holding it, the pole would actually be exerting a force on where my fingers are located. Kind of her fingers are to the right of that pole, as you can see right here. And so that's why that normal force is pointed to the right. And notice in parentheses that we have that it's the pole that is exerting that normal force on her. We have another normal force in this case. It's the normal force from the floor, and that's pushing upward, perpendicular to the floor, as we've learned that normal means. And it's on her foot, and so you'll notice where that normal force from the floor is located. Also pointing out that since we have two normal forces here, that's why it's really important to have those things in parentheses as to what is exerting that normal force. So we can differentiate between the normal force from the floor and the normal force from the pole. Lastly, we also have friction acting here, and that friction is opposite the way that she would slide. If there were a frictionless floor, you feel like her foot would slide backward as that train is accelerating forward, and so the friction force is pointed forward between her foot and the floor, and as we learned, friction is parallel to that surface, so it points to the right, parallel to the floor. Force diagrams are really useful because they can show us not only the forces, but where those forces are applied. Also notice that it talks about the relative magnitude. So the relative magnitude meaning if one force is larger or smaller than another. So you don't notice this in this diagram quite as much, but if a force is larger, we typically depict it with a longer arrow compared to a force that we know is smaller, we depict it with a shorter arrow. Now, a slight difference on a force diagram is something called a free body diagram. And a free body diagram is a force diagram, but it represents the object as a particle. So it means we're going to lose some information, so we won't be able to tell where the force is being applied. And for our current unit, that's not really all that important. We care much more about the forces that are present, their direction, and their relative magnitude. And we'll get all that information from a free body diagram. And the nice thing about free body diagrams is they don't require you to really have any artistic talent. So let's take a look at that force diagram once again. That's showing where the forces are and where they're applied. This would be the corresponding free body diagram. So you'll notice that there's a big dot in the middle of my free body diagram. And then all of those forces, the tail end of those arrows is on the dot and they point away from the dot. That's something really important for free body diagrams. All of the arrows have the tail end on the dot and they point away. In this case, the normal force from the pole has a larger magnitude than the friction force from the floor, and so its arrow is longer than the friction force from the floor. Additionally, in this specific case, the normal force from the floor happens to have the same magnitude as the normal force from gravity, and so those two arrows have the same length. We will have lots of practice drawing free body diagrams, and the ability to draw an accurate free body diagram is one of the most important steps in analyzing force situations and force problems.